hello to, I said hello to everyone's already here, but hello to those of you who are watching on the video. I'm David, I'm the coordinator of the Maths Learning Centre, and this is a revision seminar for Maths for Data Science in semester 2 2020. And because it's 2020, I'm here in my house instead of in a lecture theatre. And we've got a few people here who've asked some requests, and I'm going to talk through whatever I find. Cool. I'll mostly be working off my document camera just here. So, yeah, let's get going. People have asked me to talk about concepts related to probability. And there's quite a big section of probability in this course. It looks like this if I share my... this is the My Uni for this course. And it has quite a lot, right? There's permutations and combinations. There's various conditional probability Bayes theorem stuff. There's discrete random variables. And then further down, even further, there's continuous random variables as well. And the specific requests I've had are about counting, and also about random variables. So I might have a chat about those things. Okay. All right. So counting stuff is probably important for reasons, mainly so that if you're going to calculate probability, you know how many things you've got to choose from. Because probability is a comparison between what you want or what you observe or what you hope for, compared to all the things that could have happened. And so counting is, it's a good way to, it's a good idea to have strategies to count how many ways there are to do all the things that could possibly happen. And the strategies that you use for counting are useful for also thinking about probability situations as well. Okay, so what happens when you're counting stuff is that there is either a collection of objects or a collection of events or situations that are embedded in a story. And what the story has is information about objects or people or events. Choosing or creating objects, individuals, collections, events, doesn't really matter, lots of things. The story will contain information about whether you think about how to make the objects that you've got. I'm just going to keep calling them objects all the way. And so that's what you need to find out. The most important information when you want to count something is how to tell what the thing is and how to make it. I don't really know how to give that advice a way to write down, but we need to, in order to count, we need to focus on the story. We need to focus on what it is that makes the objects different from each other and how to construct them all. And in fact, we may have to tell our own story of how to construct the objects that we're thinking of. We need a story that constructs them all. All the objects you're thinking of, that doesn't miss any, and that doesn't include any of them twice. Well, more than once. Yeah. Sometimes the easiest way to do that is to split that into separate stories, and one story covers some of the objects and another story covers others of the objects. Okay, that's the idea. And all of your counting situations are based on creating this story of the objects. And then the thing that you count is not the objects themselves, but the stories that produce the objects. It will work better if I do an example. Okay. Right. So there are a couple of principles with counting the story, and that is that if you have each stage in the story will produce a certain number of options, and if every option at the first stage goes with every option at the second stage, then you multiply to produce the result. And that's the first principle of counting, about counting stories. And I believe your lecturer probably calls it the multiplication principle. And I'm just going to look that up. Yeah. So your lecturer talks about experiments being performed. I'm going to talk about stories instead. So, yeah. So if stage one has some number of options, and stage two in your story has M options, and every option for stage one, well, has M options no matter what happens in stage one. Then the number of options total is N times M. Okay, so as an example of that, what things could I do? I'm going to pick one of these three texters, and no, just give me a moment. I'm just thinking. I'm not going to do that at all. I'm going to make something even more mundane. So, so for example, make a code for a new computer, and you can choose the letters, you know, A, X, and M, and the numbers 1, 2, and 3, and 4, and 4, and it's going to have a letter and a number. It's going, well, no matter which letter I pick, there's, so my story goes, choose the letter, and then choose the number. And no matter which letter I pick, there's always the same numbers to choose from. So there's three options for the letter. And no matter which letter I pick, there's four options for the number. And so the total is 3 times 4, which is 12. And that's the basic idea of that. And the way I think one way I think about it is I can draw a tree diagram, which contains all of the possible stories that could have happened. I don't need to draw this, but this is sort of how I'm thinking about it. I could choose an A, I could choose an X, I could choose an M. And if I choose an A, I could choose a 1 or a 2 or a 3 or a 4. If I choose an X, I can do a 1, a 2, a 3 or a 4. If I choose an M, I can do a 1, a 2, a 3 or a 4. And these are all the stories. I go A and then 1, or A and then 2, or A and then 3, or A and then 4, or A, X and then 1, and then X and then 2, X and then 3, X and then 4. And these are all the stories of how to produce the various different things. And this one is A1, A2, and so on. all these different options, and there's going to be 12 because there's 3 of these and each of them has 4, so there's 3 lots of 4 in total. That's how the multiplication principle works. But the important thing to stop and think to yourself is, does what you do at the first stage of the story change how many options there are for the second stage? And if that's true, then you can't use the multiplication principle. Okay. So just to say that, what you do at the first stage might change exactly which options you have to choose from, but it might not change the number of options there are. And in that case, it's still okay to multiply. So I'm going to give one more example of this, and then I'm going to ask you how you're feeling. So what I'm going to do is I'm going to choose, one second. Here are some books from my shelf. There we go. Here are some books from my shelf. There's 4 of them, and I want to choose 2 of them to read. And it matters to me which order I'm going to read them in, because that's going to change my experience. So I'm going to choose one of them, and then I'm going to choose another one. And I want to know how many pairs of books can I choose out of these 4 to read. That's going to be my problem. And so let's see. 4 books. I'm going to say The Shadow Thief, which I shall call S. Nevermore, which I'm going to call N. Only You Can Save Mankind, which I'm going to call O. And Inkheart, which I'm going to call I. And I'm going to choose 2 to read in order. That's my example. And how many ways are there to do this? Okay, so here's the story. First, I'll choose a book, and then I'll choose another book. Stage 1, choose a first book. Stage 2, choose a second book. Okay, so if I choose my first book, there's 4 options to do this. Because there's 4 options to choose. And then after I've chosen my first book, there's only 3 options left for what I can choose. So if I choose S first, then I've got N or O or I. If I choose N first, I've got S or O or I. If I choose O first, I've got S and N and I. And I've got I first, I could choose S and N and O. And no matter which book I choose first, there's 3 options for what I could choose second. Now, the options are different depending on what the first book was, but there's always the same number of them. So since what I choose at the beginning doesn't change what happens at the second time, I am going to just multiply them. So the total stories is going to be 3 times 4, which is also 12. Sorry, 4 and then times 3, which is also 12. So there's 12 different pairs of books that I could have chosen. When it matters what order I choose them in. Okay, so what I'd like to do is for one of you to ask a question or say something about what I've just said.
Hi, David. So
hey.
I wanted to ask real quick. So we've obviously covered the permutation and combination equations.
Mm-hmm.
Which I try to have those memorized. So as a quick question, could you get to this answer using the permutation without repetition formula, or is this a combination or neither?
That's a good question. So I'm going to work on that. So this situation where you choose things one after another without putting them back, into the collection, and without putting back into the collection. That's what happened here. And it matters what order I choose them in. This is called a permutation without repetition. That's the sort of thing you wanted to know. It's like, what situation out of that list does this belong to?
Yep, absolutely. I had thought it was a permutation without repetition. However, choosing the proper equation for these counting problems has been a weak spot of mine in the past. So I just wanted to check that I was understanding how we should be analyzing these.
So my answer to that is that I have real trouble knowing which formula goes with what situation, and the words permutation, combination, and repetition are all too similar to each other for me to, on the fly, cope with what they mean. I know what they mean if I've got a couple of minutes and I can breathe and figure it out. But when I'm trying to go really fast, I can never remember which one goes with what. And then not only do I have to know what those words do, then I have to match the formulas up. And I'm really bad at remembering formulas. But what I can do is remember a sequence of actions that I can perform. And I can remember things that make a situation similar or different to each other. And so for me, when I do permutations, I know that each option just changes how many options there are for the second one, and I multiply all those numbers together. And so I started with 4, and then it's 3, and then it's times 12, and I don't have to use a formula for that in this situation. I can just figure it out, and that's quicker than me for doing this. But the combination one is the one that actually it is very useful to know how it has a formula for it, and usually how to make a calculator or computer do it. So the combination is when you don't care what order the things happened in. And I'm just going to have to tell you just the 3 other principles. You've got a multiplication principle here. There's actually an addition and a subtraction and a division principle as well, which your lecturer probably hasn't told you, but it's sort of there. It's sort of a problem-solving approach. And I am going to get to the combinations and permutations with and without repetition and that sort of thing. I have to organize it in this way or I forget it all. So permutation is to do with when you're trying to put these things in a specific order. And the repetition is and the combination is when you're not trying to put things in a specific order. And so it doesn't count as a different object if it's in a different order for a combination, but it does count as a different object if it's in a different order for a permutation. That's the difference between those two things. A different order counts as different, whereas a combination, a different order doesn't count as different. And then the repetition is to do with whether you're allowed to have the same your big object, which is a collection of things, whether you're allowed to have items repeated in that list. So it's either okay or not okay. And that's to do with items allowed to be repeated. So they're the things that distinguish between these. There's like these things, and then there's 2 options here as well. So that's to do with the story that constructs these objects, and it's about how the story describes whether whether the things are considered different or the same if they're in a different order. And this is about the object at the end and how to tell whether it's the same or different. And this is about the process that produces the objects and whether you're allowed to repeat items multiple times. Okay. That might help. Yeah. So this permutations with repetition is literally about a story where you choose one, choose an item, and there's this many ways. And then you choose another item, and there's this many ways again, because you're still choosing from the same list of things. It's a little bit like you're trying to make a word from the alphabet that's 4 letters long. So we've got 26 choices, and then the second letter we've still got 26 choices, and then the third letter we've still got 26 choices. And so then by the multiplication principle, since it's always n ways, no matter what happens the first time, it's going to be n times n times n for 3 of them, which is n cubed. And so that's the permutations with repetition formula. It's how many ways there are to produce, how many items there are to choose from, and then how many how many moments you want to choose it. That's items to choose. Times you do the choosing act. But this formula doesn't make sense to me, but this does make sense to me. I chose n, and there's n options for that, and then I did it again, and then I did it again, and I just had to multiply them all together. That's the permutations with repetition. Permutations without repetition, well, we've done that already. When you do without repetition, what it changes to is that, well, when you choose the first item, it's n. The second item, there's one less to choose from because you've already chosen one. And the third item, there's one less to choose from, so you've already chosen one. And so you end up with n, n minus 1, n minus 2, as long as it takes to get to however many you've got. And so with my books, it was 4 times 3. Because I had 4 to begin with and then times 3. But if I wanted to choose 3 books, it would be 4 times 3 times 2. And if I wanted to choose 4 books, it would be 4 times 3 times 2 times 1. And that thing of n times n minus 1 all the way down to 1, that's the name, that's what n factorial means. And so what that means is that your collection of items, you've ended up choosing all of them in order. And so that's the same as arranging n things. Yeah. And so now we have a shortcut. And so this is permutations without repetition. So permutations without repetition, the number of objects you've got, you just stop this calculation at that point. I'm just going to look up what your lecturer called that notation. Your lecturer called this thing, this would be permutation to 3n, this one, because we've chosen 3 objects out of n. Oh, it's a horrible notation. Who wrote that notation? In your calculator, it's actually written this way, like in a traditional calculator like this one. It's actually NPR. It's just I always lose it. I don't use a calculator for it very often. Here it is here. NPR there. I know that's not very clear, but that's what it is. So it confuses me to have them around the other way. So I don't like that, but I do just do this. And what it turns out is that if you have the whole of n factorial and you don't want this bit, then you divide by that to make it go away. And so the formula for I call it NPR, but is n factorial n minus r factorial. That's the one that you've been given in your notes. But all that means is that this is the product of everything down to 1, and this is the product of the end bit that you don't actually want. So this is the same as saying n times n minus 1 times n minus 2 times all the way down to however many until there's r of them. Yeah. So that's that. So then combinations require a little bit of extra reasoning. So if those books that I wanted, I didn't actually care what order I read them in, and I just said to someone, can you just choose 2 books out of those 4 to take on holidays with you to read? And you can decide later what order they're in. In that case, it just matters which 2 books I pick. And so my story actually ends up having 3 different stages. There's 4 books. I choose 2, doesn't matter what order. And this doesn't matter what order would come from you interpreting the story. When you looked at it and they went, and it told the story of, choose 2 of the books to take away with you, then it doesn't really matter what order they're in because they're just going to both go in the suitcase together. So if I did that, sort of this is my story. 1, choose the first book. 2, choose the second book. But the problem is that means that I know what order they're in, and I don't really want to know that. And so I need to somehow take into account that every pair of books is going to be counted twice. So divide by 2. Someone I once knew called this, in this case, the chicken counting lemma, and people call it the sheep counting lemma. If you want to count a collection of chickens, but they're all very fluffy and you can't tell which chicken is which, you can't tell where one chicken ends and the other one begins, you could get down and count how many legs you have and divide by 2, because every chicken has 2 legs, and that's what's going on here. And so I know it's going to be 4 times 3, but divide by 2. And this is called 4 choose 2. I have 4 objects. I want to choose 2 of them. Don't really care what order they're in. It's going to be, 4 times 3, because there's 2 of them, divided by the number of ways there are to rearrange 2 things. So if I had 6 books, choose 4 of them, 6 of them, 4 of them, well, there'd be 6 choices for the first one, 5 for the second one, 4 for the third one, 3 for the fourth one. But then every collection of 4 books has been counted once for every different order it could have been in. And so I have to divide it by the number of ways to rearrange 4 books. And that's what that will be. So in my calculator, it's 6C4. But this one's going to work out to 15 different choices. And when I actually ask my calculator to do that, 6C4, 15, yay! Yeah. So that choosing thing is based on this idea of dividing by, you count things too many times, and as long as everything's been counted the same number of times, you divide by how many there are. And that produces the objects that you really wanted. Now, this could have been written this way if I was really paying attention. If I did that and finished off this factorial with an extra 2 times 1, then that's 6 factorial on the top, 4 factorial, and 2 factorial. And so this is where the formula for NCR comes from. This idea, but with some extra bits to make the calculations look pretty with the factorial. There are other ways to explain why this one produces the answer it does as well, but this is how I think about it. Okay. So that's combinations where repetition isn't allowed. And that leaves combinations where repetition is allowed, and they are really hard to tell a story that produces the answer you want. But before we get there, I think it'd be a good idea to do some examples of using all the other stuff. And I will say that now that we know that when you rearrange n things, the number of ways to do it is n factorial. And now that we know that when you choose some number of things out of some other, you can use this notation, they can become steps in our story now. So we don't have to, the story doesn't have to always be choosing a single object anymore. We can have step 1, choose 4 out of the 6, and then do this next thing in the story, and we'll see what happens then. So we're allowed to now use these as shortcuts for a whole lot of reasoning that we don't have to do every time. Yeah, so I was sent an example to do. And it's this one here. I'll just share my other thing. Which one are we talking? Sorry, Hans, you just asked a question. Is this in following the permutation or combination equations? Which one are we talking about? I'll just put my screen back on.
That was actually my previous question that you answered already.
At the time. Sorry.
No worries.
Okay, so so this is a question in the in a past exam. It looks like it was probably last year's exam. A company employs 7 engineers, 4 data scientists, and 2 mathematicians. The director randomly chooses 3 of these employees to work on a new research project. How many different types of teams could be chosen? Thinking only of the expertise of each member. So when I read that story, I've got 7 plus 4 is 11 plus 2, 13 different people, and I'm picking 3 of them. And so and normally which person gets in is going to be really important, at least to the people who don't get in. And so normally I would do 13 choose 3 would be the total number of teams that I could make. But they've said to me that I'm thinking only of the expertise of each member. Then I'm actually not really talking about individual people. I'm just talking about the labels: engineer, data scientist, and mathematician. I think that's what it's asking me. I think that's difficult to understand. I feel a bit ambiguous. But I've answered question 2 already on the screen there. That one was easier for me to deal with. Taking into account of individuals in the company, how many different possible teams are there? 13 choose 2. 13 choose 3. That many. It's 13 people. And I chose 3 of them, and it doesn't matter what order they're in the team. As far as I can tell, there's no information to say that. And so I'll do it as that. And so that would be 13 times 12 times 11 over 3 times 2 times 1, which would be whatever it is. 13 times 11 times 6. I think 13 times 11 sounds familiar to me. No, it doesn't. Not at all. Apparently 858 according to my calculator. Sure, whatever. That one was easy to me, which distresses me that it was the second question, because normally the lecturer puts the first question first as the easier one, but okay. I'll just clear all that. How many different types of teams could be chosen, thinking of the expertise of each member?
David, could I interrupt you real fast?
Yeah, go.
So I just typed in n choose R 13 and 3 on my calculator, and I got 286, which is wildly different than what you got. So I'm wondering, what did I do wrong here? What exactly is there? Some part of this that I missed, right? So this should be a.
Oh no, I've done mine wrong. That's okay.
Okay.
I times it by 6 instead of by 2. Don't worry. So when I did the 13 times 12 times 11 over 3 times 2 times 1, I did 12 divided by 6 and got the answer 6. Because that 3 times 2 on the bottom is 6, right? So that's a 6 there. And I did 12 divided by 6. And somehow I thought 12 divided by 6 is 6, but actually 12 divided by 6 is 2. So this is supposed to come out to 13 times 2 times 11. That is 286. Right. Yeah.
Okay. All right. Glad I was on the right path there.
Yeah. Look, I'm glad you checked me, because we could have gone on for ages believing that it was, 3 times bigger than it should have been.
Yeah, happy to help.
For question 1 here, I'm thinking the quickest way is probably to list them. I mean, because this doesn't really fit into any of the situations we've done. So yeah, I mean, I think I can make it fit into one of the other situations I haven't talked about yet, but I could tell a story about this, right? So one story, so I would need to choose how many engineers I want, and then I would actually choose them, but it doesn't matter which ones I pick if I'm only thinking about their expertise. So choose some engineers, how many that I want, and then I'm going to choose how many data scientists I want, and then I'm going to choose how many mathematicians I want on my team of 3. Yeah, but maybe I should choose the mathematicians first, because there's only 2 of those, and there's only like 3 options for what that could have been. I just need to switch over to document camera because I don't have got enough space here. So there's 7 engineers, 4 data scientists, and 2 mathematicians. So this can be my story. Choose the number of mathematicians, and then choose the number of data scientists, and then choose the number of engineers. That's what I'm going to do. Okay, and then my list will be chosen, right? Because it doesn't matter which person is which. It would only just matters how many of each there is. Okay, and so let's see. So the number of mathematicians is either 0 or 1 or 2. Okay, and then the number of data scientists, if I have 2 mathematicians, then the number of data scientists can only be 0 or 1 data scientists. And then after that, I've got no engineers left here to choose. And in this one, I've got 1 engineer left to choose. And in fact, after we've chosen these, just however many is left is going to be the engineers. And so that's not really going to make a difference to how many stories there are. So if I have 1, the number of data scientists could be 0 or 1 or 2. And in this case, there'd be 2 engineers to choose, 1 engineer to choose, and none of them. And the number of data scientists could be 0, 1, 2, or 3. And in each case, there'll be 1 number of engineers we can have. So it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9 choices. And I basically just listed them all. I couldn't use the multiplication principle because each choice at the beginning here produced a different number of choices in the second stage. So I couldn't use the multiplication principle. I just had to list them all. And what I did is that I created a story that allowed me to be systematic in the way that I listed them all. I think this is the question that it's trying to answer. How do people feel about that?
So this is definitely one of those ones that seemed more confusing in my opinion. A little bit more tricky to set up. Now, my one comment here, now that you've explained this all makes sense. My one question is, okay, so which of the formulas does this fit in with?
It doesn't fit into any of them. Yep, doesn't fit into any of the formulas.
Got it. Okay. Yeah, because it seems a bit unique given the fact that there's not enough mathematicians to fit in the categories, that sort of throws you off
Yeah.
a little bit.
So if there were enough mathematicians to choose from, then you could make it fit with one of the categories you've been given. So I'm actually just going to talk about that now. So one of the problems was, of course, that with two mathematicians, you can't have as many mathematicians as you like. And what we're essentially making here is a collection of the letters E, D, and M. And my collection of letters E, D, and M is allowed to contain as many E's and as many D's as I want, because there's enough of them to go around, but it's not allowed to contain all the M's that I want. So, okay. But if I was allowed to have as many M's and E's and D's as I wanted, then what I'm doing is creating a list of how many of each of those I want. So if E was the number of engineers, and D was the number of data scientists, and M was the number of mathematicians, this has to add up to 3. Yeah. And so however many teams there are, if you're allowed to have as many mathematicians as you like, would be the same as the solutions to this, where these numbers are allowed to be any whole number, including 0. And so what that means is that if you have a formula for solving this, then you can do it. And there is a formula for solving this. This is a combinations with repetition situation. I'm producing combinations of things. The order doesn't matter, where I can have as many of any letter as I want. Combinations with repetition situation. And so since there are 3 in total, and they have to be spread across these 3 categories, the number of ways is 3 plus number of categories minus 1. Choose either of those things. So I get 5, choose 3, which is 10. Yeah. So this does in fact go with a story. If you really want to create a story that will automatically produce this answer, I can tell it. The story goes that when I'm trying to create this isn't the actual answer yet, because there's one option that we're not allowed to use, but not MMM. We can't do that. And so the actual number is actually 9, because we're not allowed to use this option.
Okay, so very interesting in that if you have a good handle on what the question is, you could really use this to actually work and just subtract the impossible outcomes.
So that's the subtraction principle. So the multiplication principle is if something happens the same number, if each stage of the story doesn't change the number that happens at the next stage, then just multiply. The addition principle is that if you've got one situation and another situation that are completely separate, then the total, you just add them together. And the subtraction principle is, well, if you've got too many and you've got some ones you don't want, just take them off. Yeah. So for me, it was probably quicker to just do the whole thing by hand, and there's only 9 of them anyway. But I created a system where I was sure I hadn't missed any. Yeah. So you can actually go all the way back to this story here, is choose how many M's there are. And if you're allowed to have as many as you want, if we just go back to that situation, then an instruction that you could do to your lackey who's choosing the committee for you, the team, is to say, now go and get me a mathematician. Cool. Now go and get me another mathematician. That's great. Can you switch over now to getting data scientists? Cool. Can you get me another person now? Get me a person. Right, so you can imagine that story. I mean, if we wanted a collection of, say, 6 people, then you'd be going, all right, so go and get someone. You always start with mathematicians. Go and get someone. Yeah, now switch over to the next kind of team member. Go over to the room where the data scientists are and go get someone. Like, you go get another one and go get another one. And so your instructions can be to a person are going to be this list of things of get another person and switch to another office. And so you've got a list that is just like get someone, get a person and switch. And you're going to have 3 of those instructions, and 2 of them are going to have to be switch. And so you end up with, there's going to be, person, switch. And so 2 of those instructions are going to have to be switch, and there's 5 in total, which produces this. If that doesn't make sense to you, that's perfectly okay, and we can have a chat about it maybe next week in the Maths Learning Centre at length about how that story produces the answer. But that's how this thing works as well. We can actually imagine this starting out at adding up to 0 and working our way along and saying, well, we're going to keep adding 1 in some positions, but we might have to switch to the next one. And we're going to have to add 3 ones. We're going to have to do 2 switches. And so that's going to be 5 instructions, and 3 of them have to be add a 1. So, yeah, that's that. And so that now finally produces the final formula for all of them. There was the permutations with no repetition, which was n times n minus 1 times all the way down to however many you want. Which came to the same answer as n factorial on n minus r factorial. There was permutations with repetition, which was n times, and there's r of these, which is n to the power of r. So I had trouble remembering these formulas, but I can remember these ideas because these are from the multiplication principle. There's combination with no repetition, which is n choose r, which is n times n minus 1 times whatever over r times r minus 1 all the way down to 1. And there's the same number on the top as there are on the bottom, which is the same as this. And then there's combinations with repetition, which is one of the ones that most people just have to remember a formula for. But if you can pitch it right, it also solves this problem. Solve the problem of, x plus y plus z plus however many equals total. That's if you can rearrange the way you think about the problem you've got into, I'm just choosing some numbers and they have to add up to the right thing. Whereas there's a number for each category, and this is the number in each category. That's the situation. If you can pitch it to that, then you can remember that this is the number of categories plus the total minus 1. Choose the total. Yeah. So I have real trouble with the n's and the r's. I don't know what they mean, but I can go the number of categories plus the total number of objects we want to have minus 1. Choose the total number of objects we want to have. Yeah. I've never said it in exactly that way, and I'm extremely happy because that makes sense to me. So, yeah. And anything else has to be constructed from those, and you have to tell a story that is like, actually, just let me see if there's any more to that question in that exam. I'm going to go back to sharing that exam. So to give some structure to the team, the director decides to appoint one member a research leader. How many compositions of teams are there now? So now the story could be so one, choose a leader. Actually, I'm not going to do that. I'm going to do this last one. Repeat the counting the individuals. So we can have one, choose a leader, and two, choose the other two people. So there's 13 people who can be the leader. And then no matter which leader you pick, there's 12 people left to choose, and you have to choose two of them. And so the total is going to be 13 times whatever 12 choose 2 is. Because no matter who you choose for the leader, there's always 12 choose 2 choices for the other two people.
Okay, so I think this one then turns into 858, I think, comically.
Yeah. 13 times 12 times 11 divided by 2 times 1. Yes, it does turn out to 858. Dramatic irony.
Despite the fact that we're talking about probability, I don't want to find out what the odds of that are.
No, probably quite high considering this is my second revision seminar of the morning and I'm pretty tired. So I find ones where you can tell the difference between individuals easier. And so I tend to do them first. So now we've got one member as a research leader. So I guess we could tell it, but now we can't tell the difference between the engineers and we can't tell the difference between the data scientists and we can't tell the difference between the mathematicians. So I guess my question needs to be, I have a whole, anyway, just a second. I just had this idea for this problem number 4. We could have done it a different way. Our story could have been, choose, I love it. Okay, I'm just gonna, the story could have been 1, choose the team, and 2, choose the leader. And we know how many ways there are to choose a team. We just figured it out earlier. It was, what was it, 200 and something?
It should have been 286.
Yeah. 286 ways to choose a team. And in every team, there's 3 people to choose as the leader. So there's 3 choices for who the leader is. And so the answer will be 286 times 3. Which is the correct 800 and whatever. 858. So that's an alternative way to do the same problem. That's reusing the answer to the first problem that we did, which is probably ever so slightly quicker in an exam. So let me see if we can run that same thing. What if we choose our team of 9? So there's 9 people, 9 different teams we could have chosen. And then we choose a leader. Oh, crap. If my team's only got 2 different kinds of person, like it's only got engineers or 1 different type, it's only got engineers in it, then it doesn't matter which one I pick as a team leader. So actually this isn't going to work because there's a different choice for how many, different number for how many choices there are for the leader, depending on what kind of, like what happens in the first stage. And so that's not going to work. We're going to need a different way of doing that. And so I have this feeling that we're going to have to actually figure this out just by listing them. We already listed them all earlier. Where did that go? We already listed them all earlier. So in this one here, there's only 1 choice for the leader. because they're all engineers. In this one, there's two different kinds of people, so there's two choices for the leader. In this one, there's two different kinds of people, so there's two choices for the leader. In this one, there's only one kind of person, so there's only one choice for the leader. This one has two different kinds of people, two choices, three different kinds of people, three choices, two different kinds of people, two choices. So this is a number of ways. Sorry, that's a wrong. There's actually like 1 and 2 and 1 and 2 and 3. There's all different choices for how many there's going to be. This has got 2 choices and this has got 2 choices. So we have 1 plus 2 plus that's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 ways. I just counted them directly, which seems like a lot of work for 1 mark. To me, anyway.
That definitely seems like one of the more complicated questions. I don't recall us really having too many questions styled like this in the past in this course. So interesting.
I do remember people coming to me after the exam last year in the Maths Learning Centre saying there was this really awful question about counting. So I wouldn't expect this year's lecturer to put something like that in after the experience of last year, because it is the same lecturer. If it was a new lecturer, then all bets are off, but someone who had an experience of people bombing out on something like that would probably be a bit more careful this year. Yeah, so you could have done this a different way. The thing about counting is there's usually lots of different ways to achieve it when it's not one of those simple, well, in inverted commas, simple, when it's not one of those straightforward off the list things of a permutation with whatever repetition or not, and you have to sort of do a subtraction or something, then there's lots of different ways of doing it. And so yeah, that can sometimes be a problem because everyone will do a different way and it'd be fine. So that one we probably could have done a different way. We could have said, well, let's choose our leader first, and that could be either a mathematician, a data scientist, or an engineer. And then once I've chosen them, then I have to choose 2 people out of the people who are left. And so I could have done it that way. But again, whether you choose an engineer or a data scientist gives you a different response to what happens next compared to whether you choose a mathematician. So it would all be complicated no matter what. It just stresses me that it's only worth 1 mark. Oh, wow, there's even more. Okay. The research project becomes much bigger than anticipated, and so a 4th team member is added to the team. How many different team compositions are there now, thinking of only of the expertise of each member? Okay, so just a second. We did that. Let's do it by our subtraction thing. Let's do it by our subtraction thing. So we had 7 engineers and 4 data scientists and 2 mathematicians. And now we want 4 team members. And so we could do what we did before, where this is the number of engineers and this is the number of data scientists and this is the number of mathematicians, and it has to now add up to 4. So the total number of ways is 4 total, and 3 categories. Choose 4. Oh no, 3 minus 1. It's always -1 because it's about how many separations between categories there are. So that'll be 6 choose 4, which is also 15. No, that's not 6. Yes, it is. Okay. Which is 15. But we're not allowed to have MMM, M, and we're not allowed to have MMME, and we're not allowed to have MMMD. But everything else is fine. Yeah, we're not allowed to have 4 mathematicians. We're not allowed to have 3 mathematicians. And so it's going to be taking off 3, and so therefore the total is 15 minus 3, which is 12. That's how I would attack this problem, probably. It seems very clean now that we've got an answer for the other one to run that way. Yeah. So it starts to become a bit unwieldy when you've got a bigger gap between what's allowed and what's not allowed, I guess. Yeah. It would be extremely uncomfortable if there was 3 Ds here and then we had to take into account both the M's and the Ds we're not allowed to have. Okay, so that's a lot of counting stuff. How are people feeling about the counting at the moment? Technically only got 10 minutes left, but it's not the worst thing to talk through in a revision seminar.
So I really appreciated all of that. You actually answered a question I've had throughout the course, which was about do you use permutation or combinations depending on the order. So this has been really helpful. I really appreciate that. And since this is a very this is pretty foundational for getting into probability later on, I think this was really helpful. So thank you very much.
You're welcome. Anthony, did you want me to look at any of those examples that? Oh no, they were your examples that you sent. Sorry, that's okay. All right. So just a second. I saw some other things there. Someone asked me a question. That person's not here, but I'm just going to have a check. Not that one. Sorry for everyone watching online who's going, what the hell is David doing here? Here it is. Okay. So someone asked a question too in the thing, and they're also counting problems. 6 red, 3 green, 5 blue, arrangement in a straight line. Oh, look, it's very similar to our engineers and data scientists and mathematicians, isn't it? Right. So the arrangement in a straight line. Okay. So I really want to do that first question, actually, because I think that's important. I think I've run out of paper. Yes. I'll just get some more. So we've got 6 red blocks, 3 green blocks, and 5 blue blocks. So assuming they can tell the difference between all the different colors, but the red ones are all going to look the same. So it seems to me that our description is going to need to, if we have a line of blocks, annotate the line of blocks like red, red, green, blue, green, red, green, etc. And we're doing them all in a big straight line. What would distinguish 2 lines of blocks from each other would be which positions are red and which positions are green. And so what we could do is our story could be make your line of 14 blocks and then put the blue ones in and then, put the red ones in and then put the green ones in and then put blue in every other spot. And so my story can be, let me just clear that. Actually, is it going to work if I annotate over here? Yes, oh, that's awesome, beautiful. So my story can be choose spots for the red, and then 2 choose spots for the green, and then all the rest of them have to be blue. So the number of spots for red, well, there's 14 spots total, and I'll choose 6 of them to be red. And then no matter which 6 spots for red I pick, there's definitely 8 spots left to put the green ones in. And out of those, I have to choose 3 of them to be green. And so it's going to be 14 choose 6 times 8 choose 3. No, yep, cool. So that's an answer. So there is a different answer as well, and I think your lecturer may or may not have given you a direct answer to this question. There is a different answer which we could do. We could say, well, let's just pretend that, the universe can tell which block is which, even if we can't. And so there's 14 different blocks. So I'll just clear all the drawings. So it could be there's 14 different blocks, in which case there's 14 factorial ways to arrange them. But then we can't tell which red block is which. And so we have to sort of go, well, just every possible arrangement of those 6 red blocks is been counted, however many there is, that many times, so 6 factorial times. We're going to have to divide by that because I can't tell the difference between them. And now the green blocks, I can't tell the difference between them either, so I'm going to have to divide by 3 factorial too. And the blue box, I can't tell the difference between them either. I'm going to have to divide by that too. So this is like a sheep counting story on steroids. This is the same answer. So that one there. How do people feel about that?
So my first question here is for the first one, how many possible arrangements could the child create? Why is 14 factorial? Why is that alone not the correct answer again?
Because we can't tell which red block is which. They're all the same. So that 14 factorial is the number of ways to arrange 14 completely different objects in a row. And so,
okay, so this is more. This is a combination without repetition.
It is
sort of.
sort of, yeah. So okay. Combination, yeah. It could be seen as a combination with repetition, but it's not quite. It's actually more like it's not any of those categories per se.
Mm-hmm. Okay.
It's like a permutation with repetition, except you're only allowed to have the total number of reds has to be exactly 6. So if you had a permutation with repetition, it'd be like 3 to the like there's 3 possible colors for each position. So you could have thought it that way. You could say, well, there's 3 different colors, so 3 colors for the first position, 3 colors for the second position, 3 colors for the next position, and there's 14 positions total, and it'll be 3 to the power of 14. Except that would be allowed to have 14 red if we wanted. It's allowed to have 14 green too. So it's way too many. So somehow we have to take into account the fact that, so you could see it as a permutation with repetition, but then you're not allowed to have any more than 6 red blocks. And so somehow you have to deal with that. And one way of dealing with it is to think about it entirely differently as a combination. Yeah. Okay. So now, sibling who's colorblind and cannot distinguish between red and green blocks. Well, now there's 14 factorial. And the 6 red blocks and 3 green blocks are just 9 red-green blocks that nobody can tell the difference between. So the universe could tell the difference between those 9 blocks. And so there'd be 9 factorial ways to arrange those 9 blocks if you could tell them apart. But if you can't tell them apart, every possible arrangement of all 14 blocks, 9 factorial of them they come in groups of 9 factorial, where it's the same blocks in the same position. Like it's where the 9 blocks are in different positions. 9 blocks are in the same positions but a different order, but you can't tell that it's in a different order. So you're going to have to divide by that 9 factorial. And the same goes for the 5 blue blocks. Yeah. The child insists that each green block must be placed immediately to the left of a red block. Oh, wow, okay. What the hell? Okay, so now we have the green blocks have to be next to a red block to the left. So we've got a green block has to go with a red like that, and they have to go like that. So I might as well imagine that they're glued together. Oh, what? I don't understand how to do this yet.
Well, right. So now that those blocks are glued together, we essentially we have 5 blue blocks, 3 red blocks, and then 3 green red blocks.
3
right?
green red, yeah. Okay, and so the number of ways to. Yep, I'm all good with that. Now what?
So maybe it turns into 11 factorial over 3 factorial times 3 factorial times 5 factorial. Does that seem possible?
It seems not unreasonable.
Okay, well that's good enough for me.
Yeah, okay. So there's 3 of these, there's 3 of these, and there's 5 of these. Yeah. Cool. And you can tell that a plain red is different from a green red because it doesn't have a green to the left of it. Yeah. Okay. And so there's now 11 over 3 factorial, 3 factorial, 5 factorial. That's what you were saying, 11 factorial. Yeah.
Yes. Yeah. And I just calculated that real quick. That does produce 9,240, which seems maybe suspiciously high, but.
Oh, I don't know. The other numbers are horribly high.
Okay. Okay.
14 factorial, choose 5 factorial, like 14 choose 5. Like this number here is the same as 14 choose 5. And that's going to be like 14 times 13 times 14 times 13 times 12 times 11 times 10 divided by 120. So there's the 12 times 10 is there. So 14 times 13 times 11, that's still a really big number. That's still 2002. What did you get for the other one?
Well, okay, so for 14 factorial over 9 factorial times 5 factorial, I got 2002 for that.
Yeah.
But for 11 factorial over 3 factorial times 3 factorial times 5 factorial, that I got 9,240.
Oh, I mean, it should be bigger though than the colorblind one though, but definitely smaller than definitely smaller than that one.
Okay, let me try that one real quick as well.
Where's my factorial button? There it is.
Yep. Okay. So the original one, the first one, is incredibly large at 168,168.
Yep. Yep. Okay. Yeah, we removed a lot more different things by being colorblind than we did by gluing the green and red ones together. Yep. The child places 1 block into each of 3 labeled containers. How many distinct arrangements of blocks in containers are there? Oh my goodness. What? My emotional reaction to that is what? Container A and container B. Oh no. Okay. I'm going to have to not be on the screen here for this one. So that's the situation. We've got 6 red, 3 green, and 5 blue, and there's the 3 containers that are labelled. I've labelled them A, B, and C, which is probably a bad idea considering there's already a B for blue, but whatever. And we put 1 block into each. Oh, okay. That's a little easier. So we put 1 block here, and 1 block here, and 1 block here. How many different distinct arrangements of blocks and containers are there? Okay. Cool. So now this one could be red, green, or blue. Am I on screen? Just a second. This one could be red, green, or blue. This one could be red, green, or blue. This one could be red, green, or blue. And we know which block is in which container. And it is possible to have them all green or all blue or all red, so it's no different things. Okay, so I'll choose a block to go into the first one, and it's got 3 different colors. And I'll choose a block to go into the second one. It's got 3 different colors as well. And I'll choose a block for the third one. It's got 3 different colors as well, regardless of what I chose for the first one. And so the answer is 27. Right. And this is a permutations with repetition situation. Yeah. So my story goes, pick a color to be in the first one, pick a color to be in the second one, pick a color to be in the third one. And how many colors I have to choose doesn't change because we don't run out of green ever, so that's okay.
Okay, and that fits with the permutation with repetition equation, which is just n to the power of r. So
yes,
easy.
Correct. But as I said, I can never remember that, and the effort that I take to create the story so that I can tell that it's that is the same amount of effort to just times this things together. So, yeah. Well, thank you. I'm sorry to people who I didn't get to random variables and PDFs and remainders with Taylor polynomials and stuff, but there are some revision seminars on the Maths Learning Centre website already about Taylor polynomials. There's a little bit about random variables, and you can always come to visit us at the Maths Learning Centre. We're open 10 a.m. to 4 p.m. Adelaide time, Monday to Friday, both face-to-face at the North Terrace campus and on Zoom. And I put a link to where you can find out about what the Zoom link is in the email I gave you before. Yeah, so thank you so much for coming. You've been very helpful for giving me stuff to work from, and I do wish you the best for your exam. Yeah. Thank you very much.
Thank you, David.
You're most welcome.